The presentation is going to be given by Andy Beaupre. Andy, if you could roll the slide, please. I wanted to give everybody a little bit of information about IDEX Solutions. We were formed in 1996 as a provider for the Dassault Systems family of products. We sell, implement, train all of the CATIA, Innovia, 3D Via, Delmia products that are offered by Dassault Systems. We also have an on-staff engineering services group that helps with contract placement and just offload engineering services as well. Next slide, please. Some of our customers are listed on this screen. Next slide, please. I guess we're on to Andy. With that, I will introduce Andy Beaupre of Kubotek. Andy?
Thank you very much. Thanks everybody for coming today. I was asked to go ahead and do a webinar on what we call the Kubotek Comparison Suite. And what the Comparison Suite is, it's a set of tools that allow you to compare CAD data sets. There are a few applications for the comparison of CAD data sets. The two most prominent applications for why you'd want to compare your CAD data is one for validating translations, usually within a supply chain to ensure that data is being transferred in using high quality translations so that there are no mistakes due to unintended changes in the data due to translation. The other main application is for engineering change management. In other words, comparison of Rev A, Rev B data sets and documentation of your engineering changes. So those are the two applications that we're going to look at today. The two applications for the Kubotek Comparison Suite that we'll look at today. So let's start with a little description of why would you compare your data sets. I've gone over that a little bit, but let's take a look at some of the reasons why someone would compare their CAD data. First one, and again we mentioned it, because you're translating data between different CAD applications. So you want to be sure that when you're translating that data, that the data is not changing due to the translation. That leads directly into the second bullet we see here, which is you're translating data and you need to comply with someone else's quality system and check that your data is being translated properly. And the most prominent company that we work with on a regular basis is Boeing. They have very specific requirements for their suppliers when their suppliers are using their data and translating it throughout their manufacturing processes. So in order to comply with the Boeing quality standards, their suppliers need to validate or compare their translations to make sure that they're accurate. Using a tool to detect engineering change obviously does the obvious things like eliminates the errors and human errors and risk associated with visually checking your data. It obviously can reduce the time it takes for you to check your data. It's very useful when you want to integrate some sort of supplier process for managing your translated data throughout a supply chain. And that's similar to what the Boeing application is. And obviously the obvious things, you want to use a friendly tool for communicating change, and in many cases you want a report that gives you a graphical indication of the changes in your data. So these are just some of the basic reasons why you'd want to go ahead and compare CAD data. What the comparison process looks like for comparing CAD data is pretty straightforward. Basically loading your data, finding out what contents of your files are. Once you load them into the validation tool or the compare tool, set up your compare options, things like tolerances, types of data that you want to compare, whether it be wireframe, surface, solid, or even annotation data. So those are all things that you do when setting up your compare options. And then you go ahead and execute the comparison. In other words, compare the data. And then this is where when you actually have compare results, this is where the two applications that we outlined earlier kind of start to split apart. So the compare process, whether you're doing validation of translation or engineering change order management, the compare process is exactly the same. But the two applications differ in how the information is reported. Basically, for validating translations, the output of your compare process is usually a quality document that provides traceability back to the fact that you did the comparison. Whereas if you're doing engineering change order or Rev A, Rev B comparison, you're looking to get an engineering change order or some sort of graphical document that describes engineering changes in your data. So that's kind of an outline of the compare process. If you talk about the technology that's used, at least in the Kubotek Comparison Tool, we do a geometry-based comparison or geometry-based validation. It's not a points comparison like you might see in some other applications. We've developed a proprietary technology called pattern matching, and the graphic you're seeing right now is kind of illustrates the pattern matching technology. You're seeing that as the cursor is run over the model, you can see that matching faces in the alternate model can be found. That's the idea of pattern matching. And it's again, it's a proprietary technology that was developed at Kubotek. So how does that translate into the comparison process? This proprietary technology. If you look at the comparison process, it's really a three-step algorithm. It uses pairing, which is the pattern matching we just looked at, comparison, and then a deviation calculation. So really quickly going over this slide, if you look at pairing, if you look at two models or two CAD data sets, we would use pattern matching to start to pair up the elements between the two models. If we find an element that does not compare with any elements in the other model, it automatically becomes a difference. And the example in this graphic here is the hole you see in one of the blocks. We find that difference during pairing, and it's an example of something that exists in one model, not in the other. Once we find a difference, it automatically goes into a difference list that you see here. Once pairing is complete, all the pairs then progress into the comparison, and each pair that we find during pairing is then compared using a deep geometric tolerance, deep geometric comparison to a tolerance that we set in the compare options. Those pairs that are found to be out of tolerance would end up in the error list. And then for every error that we find, we actually calculate a position of maximum deviation. So that's the third part of the algorithm. So this just kind of gives you an idea of what happens behind the scenes when two files are compared, or two CAD data sets are compared using the Kubotek validation comparison suite. So when let's first start by really getting into the nuts and bolts of what validation of translation is. So I'm going to go ahead and outline the steps for validating a translation. Then I'll do a live demonstration and show you how it's done within the Kubotek comparison suite. So let's take a look at a few slides that describe translation validation. So the challenge is to doing translation validation. Usually this is, again, within a supply chain where an authority data set is being sent from usually a major aerospace supply company. It's sent through, the data is sent down through its supply chain, and as the supply chain utilizes that data for manufacturing, it may translate it. So the challenge there is that many of the suppliers are using multiple CAD systems or multiple applications within manufacturing, which results in that authority data set being translated many times. The challenge is to be able to validate or ensure that each of those translations is accurate. And not only ensure that, but document it for their quality system. That's the biggest challenge. So we have a tool, obviously, within our comparison suite called the Kubotek Validation Tool, which provides the comparison capability that I just outlined in the previous couple of slides. And what the validation tool allows you to do is write a quality document that provides you, again, traceability back to the fact that you did that translation. So the document, just to outline the typical quality document that you might see, or the most prominent one, again, the reason why we even developed this tool is because of Boeing's D6-51991 requirements for what digital product definition at the Boeing suppliers. This is the document that when you validate a translation, if you're a Boeing supplier, you're trying to comply with this document. And you can see there's very specific parts of the document that pertain to data exchange methods. And usually they talk about translations, and you can see some of the verbiage here. Suppliers must be able to demonstrate the CAD translation process, including verification and interrogation methods used and the ability to identify known discrepancies. That's validating a translation, that 9.2.2, which is what our comparison suite provides. So what does the validation process, if you will, look like? It's fairly simple, but there's a couple of caveats to it. Usually, the aerospace manufacturer has an authority data set that it's going to send down to its supplier. The supplier has some sort of manufacturing software that it uses, obviously, to manufacture parts. That authority data set is usually read into the manufacturing software for use. When the authority data set is read, that's the translation that we're trying to validate. The fact that that authority data set was read into some other system other than its native CAD system. So the way the process works is read the authority data set into the manufacturing software and then save a copy, what we call a copy file, out of the manufacturing software. That copy file is then compared back to the authority data set. As long as they match, we can provide a quality document that says that translation was good. So in general, the rule of thumb here is that the copy file needs to be able to save a high-quality version of the data that was contained in the authority file. There are some cases, and I'll just throw this out there, there are some cases where the manufacturing software is incapable of doing that. One of the most common cases is when you have some seats of inspection software that are used in manufacturing are unable to save, let's say, boundary representation, solid and surface model data that might be found in a typical native CAD file. In that case, there are other ways to execute the validation process. The most common would be read the authority data set into the inspection software. Inspection software puts point nominals on the model, and then those are saved to the copy file. In that case, it's not a direct comparison of entity types. In other words, it's not a solid to solid or a surface to surface comparison of the CAD data. It's now a point comparison. In other words, you're putting the point nominals from the inspection software, and you're putting those onto the surfaces within the authority file, and you're making sure that they match. It's not the A answer for validation, but it is an acceptable answer in most cases. So that's an idea of translation, validating translations. Another case might be if you were archiving your data, or you were actually doing a translation for your suppliers. You could validate in-house before sending a translated neutral file downstream to your suppliers, and that's this graphic here. Where you've got your seat of native software, you obviously save the native file. You also save a neutral file, and I just, let's say, that file, for example, and you're trying to make sure that that translation into that neutral file format is accurate. So you could save each file out of your native software and then compare them, and then, again, produce a quality document that shows that translation out was valid. A couple of graphics just to explain the validation of a translation. So let me go ahead and jump over into the software, and I'll show you how it works. So I've loaded two files into the Kubotek Validation Tool. The file you see on the left is just a CATIA V5 part, and it's been translated to IGES, the file you see on the right. Generally, the files are notated as master and copy. Master being the authority data set, or the CATIA V5 file in this case, copy being the IGES file in this case. So the first order of business, again, as I said earlier, is to load the files, which we've done. The next order of business is to go ahead and set up the compare options. You can see here, without getting into too much detail, that you can decide what types of geometry you want to compare. In our case, we've got a solid model and a surface model. So we're going to want to look at surfaces or faces. So I'm going to set that up. The other thing you want to apply is a geometry tolerance. The geometry tolerance is usually set to be equal or less than the tolerance that the least tolerant file format you're comparing is able to hold. In most cases, 1/1000th of an inch is an acceptable tolerance for validating translations, especially when an IGES file is involved, as IGES is an inherently low tolerance file format. So I'm going to go ahead and compare the surfaces of these two models at 1/1000th of an inch. If you look at the two files, obviously there's some extra data in the IGES file. Since I'm not comparing wireframe or point, those will be ignored during the translation, during the comparison. So in this case, I would go ahead and execute the comparison. The first thing I'm going to do is go ahead and define my master and copy file. Obviously, my master is the V5 file, and my copy is the IGES file. You can see that master goes to the left and is denoted as such, and copy goes to the right and is denoted as such. Now I'm going to go ahead and select the geometry in the master file that I want to compare, and then select the geometry in the copy file that I want to compare. Very simple. So based on my selection, my tolerance, and my options, I've gone ahead and I've compared the two files. The red light down here indicates that there are some differences that are found in these files. Let me go ahead and display those differences. And as we saw in our graphic that showed how the compare process works, there are two lists of differences. Those geometric IDs that do not match from the master, and those that do not match from the copy. The way you'd go ahead and review these is go ahead and click on one of the errors. You can right-click and do a zoom to, and it's actually highlighted in the model. In this case, you can see that there's this O-ring groove in the master model, and if I synchronize the two models, you can see that that surface has actually fallen off in the copy. So it's an example of something that exists in the master, not in the copy. It's something that fell off during translation. If you look at some of these other differences, you can see that there's a deviation associated with them, about a 2,000th deviation. If I do a zoom to, you can see that it's this face right here is showing as an arrow. If I overlay these two differences, you can see very clearly in the overlay window. Let me zoom in so you can get an idea. It's an example of a surface that moves slightly during translation. You can see that when you overlay them. So these are all examples of differences that can be found, again, during translation. So once I've completed my comparison and I reviewed graphically what the differences are, I can go ahead now and write my quality document that would be used for my quality system. To do that, I'm going to go ahead to my options again. My report options, I'm able to choose text, HTML, or PDF. I'll write a PDF report here. And then go ahead and just write the report. And again, this is going to be a quality document that provides me with traceability back to the fact that I did this comparison. Here's what the quality document looks like. It's a very rigidly formatted document. One of the criteria that was one of the specifications that was insisted on by Boeing was that this document, when we generate it, would be tamper resistant. You can see by this certification data here, this is what we use to detect whether or not this has been tampered with. The certification data is actually an encrypted version of the rest of the report, and it's used when this document is being reviewed to detect whether or not, again, it's been tampered with. So this is all about traceability. The first thing you see here is the version of the validation tool that was used. Then again, the encrypted tamper-resistant attribute in the report. And then we've got traceability data for the master file with a picture of it, traceability data for the copy file with a picture of it, a listing of what the comparison options were when the comparison was done, and then the IDs or the space IDs from each of the components that were compared during the comparison for both the master and copy file, and then a listing of the differences that were found. You can see for a particular difference, this is IDs not matching the master. You can see right here, unmatched, ID 4771. It's a solid face, geometric face error. We give you an actual position of maximum deviation, a nominal or where that should have been, what the deviation is itself, and then how far out of tolerance it is. So that's a typical example of the type of information that's in the quality document. And the way that we provide traceability is through the ID numbers on the particular faces of the model. So let's say 6 months down the road, an audit were to happen where the auditor pulled up one of the quality documents and said, okay, there was a difference here on ID 3413. We could then open the particular file and use the tools here to go ahead and find by ID, and I'm sorry, I forgot the number, 3413. So I can find a specific surface by ID. You can see that it highlights it in the model right here. It's that particular surface. So that's how you get traceability from the quality document. And that's pretty much validation of translation. So why don't we toggle back to the PowerPoint. Actually, let me stay here. I'm going to close down this application very quickly. And let's toggle back to the PowerPoint, and let's take a look at engineering change management. So when you talk about engineering change management, we're talking about comparing two models and writing an ECO, or an engineering change order. It's usually some sort of document that has multiple screen captures in it that show a visual image of the changes, and then some sort of annotation or documentation over the top of it that describes those changes. And it's, again, documenting change. So the challenge is that traditionally, companies use a standard overlaying technique where they take the two revisions of the design and they overlay them, and then they look for bleed through in the two models. So they're visually looking over the two models for change. The problem with that is that it's not difficult to miss something. And even the smallest change, obviously, very costly if it's not caught within the proper, within the right phase of the manufacturing process. So the idea is that by using a tool like the our ECO Manager, you will find all of the changes, and whether intended or unintended, you'll know about them before you head into manufacturing. Not only that, but you can also communicate them to the various departments that need to know about them. So engineering change management is very simple. Rev A is compared against Rev B based on compare options, and then a change report is written. Now the change report is very, very different from the quality document that we saw in the validation of translation application. It's literally a PowerPoint that has screen captures captured into it that describe the different changes between the two models. So again, I mentioned this earlier, but this is a graphic that shows kind of what has traditionally been accepted as a change management process, where you've got two versions of a file, a Rev A and a Rev B. You basically manually overlay the models and try to locate change by looking at the bleed-through on the two models. Then you go ahead and manually measure the change, and then manually create some sort of document that describes the change. With the ECO Manager, we've got, again, Rev A, Rev B. We read it into the ECO Manager and define the tolerances that we talked about earlier. Go ahead and compare the two models, get results that can be organized, and I'm going to show you how that works when we get into the demonstration. And then use those results in your organization to describe change throughout your organization and to generate a graphical report that shows the changes. So again, the big thing, the main advantages of using a tool like ECO Manager are, one, we're able to assess the change very quickly, and we're able to find that needle in a haystack that you may have missed using other methods. And again, that one needle in the haystack can be very, very costly if left undetected, whether it's intended or unintended. If it goes downstream to manufacturing and you're making bad parts, obviously, that's what we're trying to alleviate. The other thing is that you can, once you know where the changes are, you can plan for them. And what we call our list of differences is called an ECO data model. We can actually take the changes that we find between the two models and organize them into folders. The folder definition, or the way that we organize those changes, could be different depending on the role of the intended user of the engineering data model. So your machining department may need a different view of the changes than your quoting department may need, etc. All of those intended or unintended changes can be organized and planned on for the specific user of the change information. And it kind of speaks to this slide where you're able to implement an ECO data model that is beneficial to anyone within the organization. So let's go ahead and see how an ECO or an engineering change comparison would take place. And I'm going to pause my screen just for a second while I get my application going. Please bear with me momentarily. Okay, so I've got my Rev A and my Rev B loaded into my engineering change, my ECO Manager product. Let me go ahead and tile these windows so we can get an idea of the parts. It's actually a component off of the landing gear, so it's an aerospace part. And again, there's Rev A and Rev B here. And if you look at the two parts, to a trained eye, you might be able to just pick up the changes by looking at the two parts. But again, that's not an extremely effective way of doing this. You may miss changes, again, whether intended or unintended, by using that methodology. So we're going to go ahead and compare them using, again, the ECO Manager tool. Again, I'll use my tools options, set up my analyze options. In this case, again, faces, and I'll use 1,000th of an inch tolerance, very similar to our validation of translation. And then I'm going to go ahead and execute the comparison. In this case, for ECO Manager, we don't use the master copy terminology. It's is and was, where is my Rev B and was is my Rev A. I'm going to go ahead and execute the comparison. And again, a red light down here indicates there are differences which we would obviously expect between Rev A and Rev B. Now for ECO Manager, my data is the same type of result data, but it's organized in a different format. This format allows me to put the data into folders, again, that would indicate engineering changes on the part. Now if I click on any one of these changes, let me do a zoom to. Okay, that's a blend change. but we're only detecting, obviously, the raw data just shows us a single blend, where if we, or a single face for that blend, where if we look at all of the change on the part, the engineering changes can all be comprised of several faces. In other words, this blend here is 5 or 6 faces. It's not a single face. So what we want to do is organize all of the changed faces within that blend into one folder and call it a blend change. Okay? So that's the idea of how you might organize your tree. There's a number of different ways to organize that tree. The easiest is what we call by connect faces. So if it's a difference and it's adjacent to another face, then those differences will go in the same folder. So let me show you how that works. I'm going to organize my differences here by connect faces. Now I've got a number of different folders. You can see if I click on the folders, for instance, this folder contains the blend we were just talking about earlier. If I look at this folder here, it contains this blend. Okay? So very, very quickly, my differences are organized into engineering changes. There's a couple of techniques you can use here. Obviously, you can rename these folders. You can drag and drop folders into different folders. And you can actually ignore parts of the change model depending on who the consumer of your engineering change model is. So let's say the changes to these times at the end of the model were not important to my consumer. I only wanted to describe the blend changes on the part, for instance. I could go ahead and create a new folder, name that no impact, for instance. I could shut off the show toggle on that, and then I could take the various folders that have the time differences in them, drag and drop them into the no impact folder, and they would not be displayed as differences. So now if I click my root folder, actually shut off the show toggle, I can shut off the show toggle, and now the only differences that are being indicated are the blends on the part. That's the idea of a no impact folder. And as a matter of fact, there's a difference in this bore here. I may want to take that and make that no impact. And then there are several holes, and I might want to take those and make them no impact also. So now the only differences described on this model are the two blends. The blend here and the blend that was added at the base of this pocket. So I've built this ECO data model that might be for a specific customer, a specific consumer of this change data. The next thing I might want to do is take this data and go ahead and put it into an engineering change report or a graphical report that I could use to again, share the information throughout to whoever needs it. So in order to do that, I would go ahead and set up my report options to PowerPoint in this case. We use PowerPoint as in the engineering change reporting mechanism. And then I can take advantage of another tool that is saved within the ECO data model, and that's this ECO properties page. These are all ECO properties. You can see the name of the property down the left-hand column. You can see that there's a variable associated with them down the right-hand column. You can also see there's a value that I could go ahead and alter as needed. And I could input my own ECO data properties. What happens is the ECO, writing an ECO report is driven through a PowerPoint template. That PowerPoint template is customizable. And you could actually use these variable definitions within that PowerPoint. So when I go ahead and generate the PowerPoint, any of my values here that were contained in my ECO data model will transfer automatically into my report. So it's a nice feature that we've added. Keep in mind, I've got a part number, change number, a name, and a date here in my ECO properties. So let's go ahead and capture an ECO report. The first thing to go ahead and do is organize the model into a view that kind of describes the change we want to capture. And let's do this blend first. And then I can right-click on the blend, and you'll notice there's this disposition toggle. The disposition refers to the color that's being used to highlight. Once a change has been organized into a folder, it automatically changes to its disposition color. In other words, it's an organizational tool. The convention is to capture it in its error color, which in our case is set at yellow and red. So I'd set it back to the error color, and then I can go ahead and right-click on the folder and click Capture. It's going to do what's called Open the Capture. It allows me to define my PowerPoint name. And open PowerPoint and prepare it to be captured to. Now I'm going to go ahead and insert this change data or this image on page 1 in my PowerPoint. Let's go ahead to my engineering change order report. You can see that data that was in my engineering change property page has been populated within the report. And you can see here on page 1, I've made a screen capture of that first engineering change. Now, okay, that's a screen capture, but let's say we want to add some measurement data to this. So it looks like the blend, if I run the cursor over the model, it's giving me some information. It's saying the is blend was 100 thousandths and the was blend is 60 thousandths. If I can produce this tooltip, if I do a control right click, I can actually add that tooltip onto the page in the engineering change report. And it goes directly over the top of where it was in the model. It's an editable text box in PowerPoint, but it's a direct measurement off of the model. So that's how we can go ahead and add the dimensional information off the model into the report. Another tool that's very useful, we said the traditional method for looking at engineering change was an overlay. We can actually use our examine window, which is an overlay of the two parts. The difference here is that we know what the difference is, where the differences are before we overlay the two parts. Okay? This examine window can also be used as a reference window. You'll notice the target box, which references the difference on the entire model. It's very useful on larger models. But we can actually save this reference view onto a page in the engineering report also. You can see here's my reference view of the part. So it positions that change on the overall part. So that's an example of how an engineering change order report is written using PowerPoint. And the other idea is that this engineering change data model can be saved into an electronic file and then shared that way as well. So that's a very, very quick overview of the Kubotek Comparison Suite and how our compare tools can be used for both validating translations or engineering change order management. That concludes my presentation for today. I thank you very much for coming, and I guess I would open it up for some questions. We'll be able to answer a few questions if you'd like before we conclude.
Does anybody out there have any questions for Andy? It doesn't sound like it. Andy, I think there's one more slide. Or maybe not.
Yes. Sorry about that.
Yeah, I just wanted to give you different ways you can connect with IDEX Solutions. My name is Susan Crowden, and there's a variety of ways you can connect with us. If you have further interest in the Kubotek product, we'd be more than happy to assist you with any of those questions. So with that, I'm going to thank Andy for a great presentation, And we will see you next time on the next IDEX webinar. Thanks, everyone.
My pleasure. Thanks, everybody.
Goodbye.